The machine built to find clean new physics keeps producing one borderline signal that refuses to go away or turn into a discovery. For nearly a decade, measurements of B-Meson decay at CERN showed electrons and muons behaving differently when the standard model says they must behave the same. The question is simple. Why do B-Mesons decay into muons less often than they decay into electrons? By the end of this video, you will know what the data eliminates from the old explanation, what the measurements still cannot account for, and why the answer matters even though the strongest signal has softened. The spark is this. The standard model predicts that the ratio of these two decay paths should be almost exactly 1.0, but the data kept showing something closer to 0.85. That is not decoration. It is a direct contradiction of lepton universality, the rule that electrons, muons, and tau leptons must interact with forces identically apart from their mass. If the ratio stays below 1 after all corrections, something unseen is pulling on muons differently than electrons. The old model has no room for that. Here is one concrete reality check you can hold on to right now. B-Mesons are so rare and unstable that they decay in less than a trillionth of a second, which means even a tiny shift in their behavior acts like a high-precision sensor for particles we have never seen. The standard model is the most successful theory in physics. It explains 3 of the 4 forces, predicted the Higgs boson decades before discovery, and has survived every direct test the Large Hadron Collider has thrown at it. But it is also incomplete. It does not explain dark matter, dark energy, or why neutrinos have mass. Physicists have known for years that something must exist beyond it. The question is where the crack will appear first. For a long time, B-Meson decays looked like the place. Lepton universality is not a minor footnote. It is one of the core symmetries of the standard model. Electrons, muons, and taus differ only in mass. An electron weighs about half a mega-electronvolt. A muon weighs 106. A tau weighs nearly 1,800. But when it comes to how they interact with the weak force, the photon, or the gluon, the standard model says they must be identical. If you replace an electron with a muon in any interaction, the probability should stay the same once you correct for mass. That rule is called lepton universality, and it has been tested thousands of times across decades. Until recently, it had never clearly broken. B-Mesons are particles made of a bottom quark bound to another quark. They are produced in huge numbers at the Large Hadron Collider, but they are unstable. They decay almost immediately into lighter particles through pathways governed by the weak force. Some of those decays are common, others are incredibly rare. The rare ones are the most interesting because they involve quantum loops, places where virtual particles briefly flicker into existence and influence the outcome. In the standard model, those loops are filled only by known particles: W bosons, Z bosons, top quarks, Higgs bosons. But if an unknown particle exists, it could also appear in the loop and shift the probabilities. That is why rare decays act like windows into hidden physics. One of the cleanest tests is the ratio called R of K. It compares how often a B-Meson decays into a kaon plus an electron-positron pair versus a kaon plus a muon-antimuon pair. The standard model predicts this ratio should be 1.00, give or take a few parts per thousand, because electrons and muons should behave the same. In 2014, the Large Hadron Collider beauty experiment at CERN published the first measurement of R of K. The result was 0.745. That was far below 1. The statistical uncertainty was large, so the result was interesting but not definitive. Still, it was the first hint that muons might be suppressed. Over the next few years, more data came in. The ratio kept sitting below 1. By 2017, additional measurements of a related ratio called R of K star showed the same pattern. The anomaly was not isolated to one decay channel. It was appearing across multiple modes. Physicists began to take it seriously. In 2021, the Large Hadron Collider beauty experiment released an updated R of K measurement with much more data. The result was 0.846, still below 1. And the deviation from the standard model reached a significance level that some reports called 3.1 standard deviations. For a brief moment, rumors swirled that the result had crossed 5 sigma, the gold standard threshold for claiming a discovery in particle physics. 5 sigma means the chance of a fluke is roughly 1 in 3.5 million. The actual significance was lower, but the tension was undeniable. The result was not a smoking gun, but it was loud enough to be heard across the field. If the suppression was real, it meant lepton universality was broken. That would require new physics. Theorists proposed explanations. One candidate was the leptoquark, a hypothetical particle that carries both quark flavor and lepton flavor. In some extensions of the standard model, leptoquarks can couple more strongly to muons than to electrons, which would naturally suppress muon production in B-Meson decays. Another candidate was a Z-prime boson, a heavy cousin of the Z boson that only interacts with certain lepton families. Both ideas have been around for years, but the beauty anomaly gave them fresh motivation. The excitement was not just about one measurement, it was about a pattern. Multiple decay ratios, measured independently, all seemed to point in the same direction. Muons were being treated differently. Global fit analyses combined hundreds of measurements from different experiments and decay modes. Even when you averaged everything together, the data still preferred a scenario where muons were suppressed by a few percent. That kind of coherence across channels is hard to fake with statistical noise. But there was a problem. Measuring these decays is extraordinarily difficult. Electrons radiate energy much more easily than muons when they move through the detector. This effect is called bremsstrahlung. When an electron loses energy to radiation, it becomes harder to reconstruct. The detector might miss it entirely, or it might misidentify the particle. That means the efficiency for detecting electrons is lower than for muons, and if you do not correct for that difference perfectly, your ratio will be wrong. The Large Hadron Collider beauty collaboration knew this from the beginning. They applied corrections based on simulations of how particles move through the detector. They calibrated those simulations using control samples of real data. They cross-checked their methods with independent techniques. But the corrections are not perfect. Small mismatches between simulation and reality can bias the result. If the simulation underestimates how much energy electrons lose, the measured ratio will be too low, which would fake a violation of lepton universality. In 2022 and 2023, the collaboration released new results with improved analysis techniques. They used better models of bremsstrahlung. They refined their calibration samples. They reprocessed the data with updated detector alignment. The result changed. The new R of K measurement was 0.949, much closer to 1. The tension with the standard model dropped to about 1 standard deviation, which is statistically insignificant. The anomaly had softened. It had not disappeared entirely, but it was no longer strong enough to claim a discovery. The 5 sigma moment never came. Some measurements of R of K star still show mild tension, but the overall picture is now consistent with the standard model, within uncertainty. The story could have ended there. The anomaly was a fluctuation, or a subtle calibration issue, and the standard model survived again. But that conclusion is not as clean as it sounds. The data did not prove the standard model is correct. It proved that the current measurements cannot rule it out. Those are different statements. The standard model prediction for R of k is 1.00. The measured value is now 0.949, with an uncertainty of about plus or minus 0.04. That means the true value could still be as low as 0.91 or as high as 0.99. A value of 0.91 would still represent a real suppression of muons, just smaller than the earlier data suggested. The measurement is not precise enough yet to close the window. The question is not settled. It is constrained. What the newer data eliminates is the large suppression scenario, the one where muons are suppressed by 15 or 20%. That version of the anomaly is gone. What the data cannot eliminate is a smaller suppression, something on the order of 5%, which could still be real and still require new physics. The difference matters because many new physics models predict effects at exactly that level. Leptoquarks, Z-prime bosons, and other beyond standard model particles do not have to create huge signals. They can create small ones that only become visible with enormous data sets and exquisite control of systematic uncertainties. The Large Hadron Collider is now in run 3, its third major data-taking period. The machine is running at higher energy and higher intensity than ever before. The Large Hadron Collider Beauty experiment underwent a major upgrade in 2022 that allows it to read out data 40 times faster than before. That means it can collect far more B-Meson decays and measure R of k with much smaller uncertainty. If there is a real 5% suppression hiding in the data, run 3 should find it. If the ratio is truly 1.00, run 3 should prove it. Either way, the question will be answered. But there is another layer. Lepton universality is not just tested in B-Meson decays. It is also tested in the magnetic moment of the muon, a completely different measurement done at Fermilab in the United States. That experiment also shows a tension with the standard model. The muon magnetic moment is about 2 parts per million higher than predicted, and the deviation sits at around 4.2 standard deviations. If both anomalies are real, they might be caused by the same new particle. Theorists have built models where a single new force, or particle, explains both the beauty anomaly and the muon magnetic moment. Those models make specific predictions for other measurements, like the decay rates of tau leptons or the properties of rare Higgs boson decays. None of those predictions have been confirmed yet, but they have not been ruled out either. The pattern is still open. What makes the B-Meson story so striking is not that it found new physics. It is that the machine built to find new physics keeps producing borderline signals instead of clear answers. The Large Hadron Collider has been running for over a decade. It has collected more data than any particle collider in history. It discovered the Higgs boson, confirmed the standard model in exquisite detail, and set limits on thousands of hypothetical particles. But it has not found a single unambiguous sign of physics beyond the standard model. Every hint has faded. Every anomaly has softened. Every 5 sigma dream has turned into a 3 sigma maybe, or a 1 sigma nothing. The beauty anomaly is the most famous example of that pattern, but it is not the only one. The diphoton bump at 750 giga-electron volts disappeared. The diboson excess at 2 tera-electron volts went away. The top quark forward-backward asymmetry resolved. One by one, the tensions evaporated as more data arrived. That does not mean the standard model is complete. It means new physics, if it exists at the energy scales the Large Hadron Collider can reach, is hiding in places that require extraordinary precision to see. It is not a dramatic discovery. It is a slow, grinding campaign of measurement and uncertainty reduction. The B-Meson program is exactly that. It is not looking for a new particle that jumps out of the data. It is looking for a tiny shift in a ratio, a shift so small that it takes years of data and constant refinement of systematic uncertainties to resolve. That kind of physics is harder to communicate, harder to fund, and harder to sustain public excitement around. But it is also where the next breakthrough might come from. History shows that many particles were predicted through precision measurements long before they were seen directly. The top quark was inferred from loop effects and other decays years before it was produced at the Tevatron. The Higgs boson left fingerprints in precision electroweak data decades before the Large Hadron Collider found it. Indirect discovery is real discovery. It just takes longer. So here is the answer to the title question. Why do B-Mesons decay into muons less often than electrons? The current data says they might not. The strongest version of the anomaly, where muons are suppressed by 15%, is eliminated by the latest measurements. But a smaller suppression, 5% or less, is still allowed by the data. The standard model predicts no suppression at all. The measurements are now close enough to that prediction that we cannot claim a violation, but they are not precise enough to confirm the prediction either. What remains unresolved is whether the small remaining tension is real new physics or the last echo of a systematic uncertainty we have not fully controlled. The verdict changes this. The beauty anomaly is no longer a 5 sigma hope. It is a precision measurement campaign. The question is not whether we will find a dramatic signal tomorrow. The question is whether the ratio will stay below 1 as the uncertainty shrinks, or whether it will drift up to exactly 1.00 and close the window for good. The data from Run 3 will decide. Until then, lepton universality remains one of the most precisely tested and most carefully watched symmetries in all of physics. The fact that it has not clearly broken yet does not mean it never will. It means we are still looking. If you want to follow how this resolves, keep an eye on the Large Hadron Collider beauty results over the next few years. The final answer is coming.